Click the bell icon to get latest videos from Ekeeda.
Chapter Nature of Chemical Bond, and we are doing the topic determination of molecular structure of phosphorus trihalides. Hello friends, in the previous lecture we have talked about the molecular structure of basically bromine pentafluoride, and in that case we have also got to know that what would be the bond angle or what would be the expected geometry of that structure. And now similarly on that basis we are going to talk about that is what is the molecular structure of phosphorus trihalides. So let us talk about it using VSEPR theory. So now in this lecture we are going to determine the molecular structure of phosphorus trihalide using VSEPR theory. So talking about phosphorus trihalide, in this case basically we will get to know that is the phosphorus is the one which is basically acting as a central atom in the overall structure, and that is the reason that for which we have to understand that what would be the electronic configuration, because on that basis only we could easily judge or we could easily determine what would be the structure of the overall molecule and what would be the bond angle or what would be the basically the structure of it. So that is all dependent on phosphorus depending on its lone pair of electrons. So that is what we are going to learn about VSEPR theory, as well as we are going to apply that theory in this determination of molecular structure of phosphorus trihalide. So now let us talk about that what is the electronic configuration of phosphorus first. So now talking about phosphorus. Phosphorus is the one which has an atomic number of 15 over here. So I would write it over here as atomic number 15, and I could say that is the electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p3. So this is how we can write the electronic configuration of phosphorus over here, and so this is the one which is present in the ground state. So let us analyze that what would be the number of that is orbitals that are present in it. So let me discuss about the last orbit of it, and that is the third orbit, and for which that is the valence shell that I am talking about. And let us understand that how many that is electrons are present in the s orbital, while that of in p orbital. And let us discuss about it by giving the electrons to it. So therefore this is basically 2 electrons that are present over here, and here basically 3 electrons. So that is this is it what we have made to understand. And if I would say in this manner, that is if we have included that is trihalide, so that's the reason that we could say basically each halide, as we know that it consists of one unpaired electron in its outermost shell or outermost that is orbital that I am talking about in that manner specifically. So everyone can accommodate over here, and that is how the hybridization would also be in like that of the sp3 hybridization. And that is what we could say that the valence shell of the phosphorus, it will consist of, earlier it has basically 5 electrons in the outermost shell, and because of the inclusion of that of the halogen atoms or 3 halogen atoms that would be occupied in this basically orbitals, so that will make an overall of 8 electrons in its outermost shell, and that is how it can complete its valency. But let us understand it by giving the few examples that I am going to talk about. So the examples would be like phosphorus trihalide, like that of I would say like PF3, PCl3, PBr3 and Pi3. So this all kind of halides that I am going to talk about, and the geometry it would be like same, but there would be effect of somewhere the effect of this lone pair of electron. So how does this lone pair of electron that is has an effect on the bond angle of it, that is also we are going to discuss about in this lecture. And let us talk about the first one, that is talking about PF3. That is phosphorus trifluoride. This is what we are going to talk about, and let us understand it with the help of the that is valence shell of the phosphorus. And in this case we have got to know that is the valence shell is basically 3s of the phosphorus, while this is of I could say like 3p of phosphorus, that is what's been involved. And the s orbital basically consists of 2 electrons, as we know. While talking about the p orbital, when it comes to the electron of the phosphorus, then it consists of basically 1, 2 and 3 electrons. But here we are talking about that is only phosphorus. But what if we are talking about fluorine? And fluorine is what we have discussed in our previous lecture also, that is the electronic configuration that we have. So now talking about fluorine, as we know, that is fluorine is the one which has basically an atomic number of 9. So let me recall it again. So this is 1s2, 2s2 and 2p5. So if I mention the orbital of this one, so in this case basically we'll get to know that is, so this is the example that we have did earlier also, but let me explain it again so that in kind of any kind of doubt if you have, it would be clear. So it consists of basically 1, 2, 3, 4 and 5 electrons, and this is the orbital of, or I could say like pz orbital, that would be involved in basically bonding over here, and that is what we could say, that is I would represent the electron of fluorine in this one, like in this red ink. So therefore this is the electron of first fluorine, second fluorine, and this is the third fluorine. So this is how we have got the structure of it. But meanwhile, if you'll observe, then this is the hybridization that we will get. So the hybridization of basically the phosphorus that it would be involved is basically, we could say that it is S and 3p, or I could say like sp3 hybridization. So this is the bonding pair that we have got. This is the bonding pair, this is the bonding pair that we have got, even this is the bonding pair, and this is the lone pair. So making this to be totally known as the valence shell. The valence shell consists of basically now, as we could see, that 8 electrons, and that plays a very vital role in giving the geometry or giving the bond angle of it. So talking about this one, let me talk about the structure of it. So if we expect that the sp3 hybridization is being showing by that of the phosphorus, so then the expected structure, it would be basically, I would write it over here. So the expected structure or the expected geometry, if I would say, that would be basically that of a tetrahedron. So that is what we have got. So we'll get basically tetrahedral geometry. So then we know that phosphorus is the one which consists of that is a lone pair also. So that this is the lone pair that it has. And according to VSEPR theory, obviously that will have an effect on the bonding pairs, and the structure would be like, it would be changed. So let me talk about this one. Coming back to the phosphorus, and the structure would be basically, this is the phosphorus that we have, and it is consisting of it is making a bond with that of 3 fluorines. So suppose if this is the fluorine atom, and this is the second fluorine atom, while this one is the third one. Since I cannot draw the 3D diagram in this one, so let me tell you that the 2 fluorine that would be on your side, and one will be on my side, so making it like a pyramidal shape. But meanwhile, if I am talking about there is a lone pair of electron also, so therefore the lone pair of electron that would be present on the phosphorus. So I am just representing it like this one. So if I have to mention the structure of it, so I could say that it would be like that of a tetrahedral geometry. But in this case, basically, in actual practice, the only thing that is the phosphorus has been remaining, the fluorine, the 2 fluorine that are on the plane, or they are above the plane, and one is below the plane, and that is how we could see that again a pyramidal shape has been occurring. So that is what we could get over here. And but talking about the bond angle, so this is the lone pair of electron on phosphorus, and that is what it will have an effect on the bonding pairs. So that will have an effect on the bonding pair, and we could say so since fluorine is the more electronegative atom in this case, and also in the whole halogen family, so that will have an effect that it will try to grab the electron towards itself, and that makes the phosphorus that has an electron pair, so now that will spread easily. So while spreading or while we know that obviously a lone pair of electron that will have an effect on the bonding pair, and that is how the bond angle, which was been expected, that because it is showing the tetrahedral geometry, obviously then the bond angle would have been basically I am talking about the bond angle. So the expected bond angle would have been basically 109 degree and 28 minutes. That is what the irregular tetrahedral geometry is having a bond angle that we have discussed in the geometry of that is methane, and in that case we have also got to know that is 109 degree and 20 minutes is the bond angle of that. And but meanwhile, talking about this structure, because fluorine is more electronegative, and obviously this two will have or this two electrons or I could say that the lone pair of electron will have an effect on it. So that's the reason that the bond angle will now be reduced. So from 109 degree 28 minutes, it has been reduced till 97 point, or I would say like in this way, like 97 degree and 8 minutes. So this is the effect that it happens on that is the bond angle, because of this lone pair of electron and because of the electronegativity also, because that is what we are going to we have discussed in a separate way, that is what is the bond angle of phosphorus trihalides, different phosphorus trihalides. So this has an effect on the fluorine, depends on its electronegativity and depending on that is the lone pair of electron that has been present on the phosphorus, and this is the structure as well as we could say the bond angle of it. So similarly we could say like that of if I talk about phosphorus trichloride, that is PCl3. So again let me draw the structure of it so as I could make you understand. So that could be written as, suppose this is the phosphorus that we have, and again if I am talking about the Cl bond, so again that will have the regular one, like regular structure that we have discussed about, like PF3, and it will have basically one lone pair of electron on phosphorus. Again the bond angle, because it will also show sp3 hybridization, and the bond angle it will be 109 degree 28 minutes, but because this lone pair is present on the phosphorus, as well as it will have an effect on the bonding pair that I could see that you could see over here in this way. So in this case basically that will have an repulsion, they will repel each other, and that is what VSEPR theory is, and the bond angle will be reduced, it will reduce from 109 degree 28 minutes, but not like that of the fluorine bond angle that we have discussed, like the bond angle of phosphorus and fluorine. So it will be basically, it will be reduced to, that is what I want to express in this way, that is the bond angle that we have got to know, it is basically 100.3, or I could say 100 degree 3 minutes. So this is what we could get in the bond angle of PCl3. So that is what we could get. And similarly if we are talking about that is a PBr3, so let me talk about here in this way, that is, so this is PBr3 that I am talking about, and again it consists of a lone pair of electron here. And now the bond angle of this, because bromine is the one which is very much less electronegative compared to that of fluorine and chlorine, obviously then there will be no that much repulsion compared to that of fluorine and chlorine, and that's the reason the bond angle between this is basically, it is found to be 101 degree 5 minutes, and that is what I was talking about. And talking about the last one, that is when phosphorus is combined with that of iodine so as to form phosphorus trihalide, and because of the lone pair of electron, the bond angle is now been basically 102 degree. So this is 102 degree, that is the bond angle of between iodine, phosphorus and iodine, and this is how we have got to know. So in this case basically we have observed that because of the lone pair electron also, as well as because of the electronegative of that halogen atom, that will have an effect on the bond angle, and meanwhile the structure it's almost remains the same, having basically a geometry, the geometry will remain the same, only the difference will be in the angles, and that is what we have got to know over here. And as we move from that is PF3 to PI3, the bond angle actually increases in terms of like from 97 to suppose 102, but still it has been expectedly, we have thought that it should be basically 109 degree and 20 minutes, but it has been reduced because of the VSEPR theory that we have understood, and because of the lone pair that we have discussed in our earlier lecture. So thank you friends for watching this video. I hope you have understood this lecture very clearly, and you share this video with your friends, and don't forget to subscribe to Ekeeda channel. Thank you so much.